Hi, I'm Tom and I talk about code. Welcome to another compiler building live stream. Today, working more in Rust, we're going to try and optimize my compiler to actually use registers a bit. And I'm going to draw you a picture of what I mean by this. So currently, if I have a function like this, if I have a function, we'll just say func, foo. Actually, I wouldn't say func, because that's not how my language works. Foo. Actually, no, and critically, it's going to be a function that returns an int. Okay, and it only has one line in it. It return 5 plus 3. Okay, drawing under the pump is apparently very, very hard. How does this get compiled? What do we compile this into? Currently, and what do you think this should get compiled into, right? What would this look like? Well, currently, my machine does something really, really silly. Okay, currently, my machine will load an immediate into, I think, A. So it'll load 5 into A. It'll load, and then it'll push that onto the stack. I think. Yeah, it must do it like this. Let me double check how it works. I was confident that I knew what I was doing in this intro, but suddenly I'm doubting it. So let's double check with my code. Let's double check with my code. What is going on here? I didn't go into the right directory. We're off to a flying start today. Okay, here we go. So binop. That's the wrong expression. I want codegen expression. Bin op. So if we add, yeah, so these things get pushed onto the stack. So essentially, it will load an immediate into A, push A, load an immediate into A, that is 3, push A, and then it'll use my stack add instruction, which will take the top two things off the stack, add them together, and then push them back onto the stack. So basically, this essentially does 3 pushes and 2 pops, which, if you're building a stack machine, is okay. But this is a little bit cumbersome, a little bit unnecessary. See, and probably longer than it needs to be as well. What I think this should happen, and also, sorry, an important detail is that when we return in the A register. So we then also need to do one final pop. So it's actually 3 pops. So it would then also, in addition to this, be pop A. What should this look like? How should we do this, right? So this is bad. What if we want a good? What would good compiled code look like? Well, first off, we could use the fact that we return in the A register, right? So let's start with the same instruction. Let's load an immediate into A. Let's load 5 into A. And then there's 2 ways we could go. Let's say there's a fork in the road here, right? Depending on how smart we want to be. The dumb smart thing is that we would then load an immediate into B. We would load 3, and then we would add, store the result in A plus B, right? 3 instructions. This would be all we'd need. And the result can just go into A, because then we return from the A register. So instead of 1, 2, 3, 4, 5, instead of 6 instructions with 3 pushes and 3 pops, we would just have 3 instructions, uses 2 registers, simple and good. But actually, because this is such a small number, because this fits into an add immediate instruction, we could be even smarter and actually just generate an add immediate instruction and say that we just want to add, 3 onto the A register. So we could actually do this with 2 instructions if we want to be really clever. Now, this is probably the goal of today's stream. This would be a fun optimization to do in the future, and I don't think this is much harder. It just requires a branch. So this is basically the gist of what we want to do. Now, let's look at something even sillier. Let's say we have a second function called bar. Say we have a second function called bar, which also returns an int. Okay, and all bar does is call foo and return it. Okay, let me just move this over. Writing is a struggle. So what happens when we generate this code? Well, we're going to do all of the stuff to call foo, and then we're going to have a result in the A register. But to actually return it, we're going to have to push it onto the stack and then pop it back into the A register. And that is what I mean by this, right? So anytime a function returns, it returns in the A register. If we then return the result of that function immediately, we can't like my compiler isn't smart enough to know that, yeah, this thing's already in the A register, don't do any work, just return, don't push any extra stuff. So this is the first goal. I think this is going to be simpler, but we're going to have to think about this as well while we do it. These two things are very closely related. So this is the motivation, this is what we're going to be doing today, and I don't really know how we're going to be doing it. Let's just do a stash real quick. Let me just clean up my Git directory and make sure we're ready to go. Let's make a new branch for this, because this is going to be significant. We'll call it opt for optimization, and let's start by looking at compile expression. Now, compile expression is called recursively. It calls itself. For example, bracketed is fun. Compile expression. So if we have a dereference, we have to compile an expression as part of that. If we're calling a function, we have to compile each of the arguments as an expression. Now, in this case, we actually rely on the fact that compile expression always pushes to the stack. So this is gonna have to be more complicated here. We can no longer rely on the idea that compile expression will always push to the stack. We're gonna have to either tell compile expression to push to the stack or check which register this expression has been placed into. So that's gonna be significant. Similarly here, we do this compile, but again, we just assume that compile expression pushes to the stack. This is a precondition or like the guarantee that compile expression makes, so that then when we actually compile this stuff, we know what we're doing. If type of t, yeah, when we have like the pointer thing, which is fun. I forgot about this. Oh gosh, this is going to be very interesting. God, I didn't even think about this. So as you can see, there's quite a few places where we call compile expression. Array dereference is a fun one because the index, we rewrite it as a deref and then compile it. But deref is a fun one in its own way. Deref, compile expression. We compile the expression. Well, we compile it and then we do extra stuff with it. We do extra stuff with it. So the fact that everything ends up on the stack is a little bit of a problem here, right? Like this is running, this is the antithesis of what we want. And this is essentially the problem. So this needs to no longer return everything on the stack. So basically we're gonna need some extra information that gets passed through here. Let's make a type that can keep track of this. Let's make a struct, let's call it register state. Maybe register state sounds like a sensible name. And this will have a map, maybe hash map from register to something, which will have the current state of each register that we're interested in using. So as we go through the code, for example, we could say, instead of having to put this immediate into the C register, so previously I used the A register in my code example. We put this into the C register, which is kind of my go-to burner temporary register. So instead of this, we would kind of say, if state, so we'd say something, we'd want to ask, has free register, right? We'd say something like this. We'd want to know if the current state has a register free, and if it doesn't. Now, I don't know if it would be better. See, and this is annoying because there's 3 forks here, so maybe it's better to say it here, right? So, would maybe say let target reg equal. So kind of, we could say like get free register, but if we can't get a free register, so I guess unwrap or, I think. basically say, try to get a free register, otherwise always use register C, because that's our boner temporary register. But then we would need to say that register C has been clobbered. Okay, do we always have to leave a register free? Potentially. Potentially. So what does this look like? So yeah, so let's build this around the idea that register C is never a valid option. Because basically a register can be in a couple of states. So let's, I guess register state's a bad name, isn't it? Let's just call it state. The state of the current expression. Let's make an enum called register state. And let's think about the states, right? One would be free. Nothing is currently using this register. Nothing desires to use this register. It is an open register. It can be used for whatever. Then there would also be occupied, which is like if we're compiling a binary operation, the right-hand side of the binary operation has been placed in register B. The left-hand side, which then gets compiled next, cannot use register B. There is already something in register B that's significant here. Don't touch it. And then I guess there'd be another thing, which would be like desired, maybe, which is like we're compiling the right-hand side and we want to put it into register B, but the children of that expression, right? So everything up until we finish that expression can use register B, right? Because it's a sub-expression, because expressions don't leak out like that. So maybe, but is there a meaningful difference between desired and free? Yes, because we can't, if we're doing a binary expression, for example, we can't end up with more, like we can't have more things in flight than there are registers aiming for registers. If there are no desired registers left, that has to go on the stack. Let's think about this, right? Let's see if this kind of structure works. I think it does. I think this is okay. So something like compiling a literal int, that can use a desired register because as soon as we're done, the state doesn't change, right? Except it does. It leaves something in there. It leaves it occupied. So I don't know what the semantics of desired would necessarily be. So I think I need to draw more pictures. I think I need to plan this out a little more. So let's look at an example. Let's think about how we would do let a equal 7, let b equal a plus 19, let c equal foo a, return a plus b plus c. Okay. So let's imagine this function. Let's imagine this big old block. Now, so we have our registers, let's say A, B, and C are our general purpose registers. They are all free. And then we do this line. We come down here, we want to load an immediate into a variable. We can do that. We would say, well, actually, we have to put it into this slot, but that's okay. That's okay. So we could say, after this line, that A is occupied, it gets the literal 7 by, let's call it lit 7. Okay. Now we come down here. B, A is still occupied. A is still occupied. The hard thing here is we don't really have a way of knowing when A stops being occupied other than the function ends. And that's okay. We can just do that. This probably means that most of our code would still devolve into stack, but it means that small functions could be very efficient. The lack of this kind of lifetime analysis of knowing that A you know, in this case, A is used on every line. But what if A was only used here and then we could drop it, right? That's when you can make really useful optimizations. But I think this framework would allow this as well, right? Saying, basically just tracking this, because then at some point you could do further analysis and say that at a certain point the state of A changes. I think this would work. I think this would work. So B, A plus 19. So to do this, we would need... So let's say... Because this is one of these cases where... Actually, there's two things going on here. This isn't just the literal 7, this is also the variable A, right? So, this is the hard thing, this is the hard thing about this. So, B, we could say... Well, there's two steps here, right? There's two steps here. There's two steps here. Okay. So this needs to break out. So A plus 19. 19, we can load, let's say B is going to be occupied by literal 19. And then when we want to deal with A, we can already see that this is in reg A, so there's no work to do. So then when compiling the binary operation, we know we've already got these things in registers. So this can be compiled down into... so we have two operands, so plus needs a destination and two numbers to work on. Let's call them A0 and A1. We have A0 and A1 in registers. This is A, this is B. How do we know what we can use as the destination? Because B currently has just a literal, we can probably override it, right? We can probably just nuke it. This implies there's more complexity to my state than I had realized. Sorry, I'm getting a phone call. Give me 1 second. Gosh, work. Okay, so this feels like a system that I can work with. This is really blind coding, but I feel like this is a system that we can work with. A literal can always be overridden. I think that's what I'm getting at. But how do I know? How do I know this scope? How do I know that this literal... Well, a literal is only ever going to be used in one place. So, destination. So if we're looking for a free register, we could get C, but we should get the register already involved in this calculation. So basically we should ask, can use A... No, because it's already assigned to a variable. B, yes, because it just has a literal in it. And we could decide that the result of this goes in B. So we would end up with add B, A, B. And then we would also say that B would be occupied by the variable B. Lowercase b. Okay. Now we're going to have a function call, and function calls break our whole state, right? Because we kind of want them to be a blank canvas. So I guess the obvious thing to do here, right? The obvious thing to do for a function call is, that's not the color I wanted either. The obvious thing to do for a function call, before we do a function call, we push occupied non Right, so there's kind of a difference here between a register occupying a variable and a literal occupying a variable in terms of how much kind of precedence, in terms of how much weight they carry. And then after we have to restore it, so we would end up with A in register A and B in register B. And then for compiling this, and C would come back in register A. And that's okay as well. So the restore is interesting here too. Okay. So there's a lot of stuff going on here. Right? Because when we would restore from a function call, we're basically saying that A has the result of this that we could assign to... Okay, I think I'm getting it. I think I'm getting what's going on. I think I'm getting what I'm getting at here. So... there's a couple of different states here. Let's say a variable with a name, just a name. What about struct fields? We'll go with a string name, and if it's a struct field, we'll just concatenate them with dots, and we'll live with that. There may be weird aliasing problems, but that's okay. There's also the invalidation here, right? Where if we were to somehow pass the address of register A into a function, like rather than the value, the actual address, then that could be modified and we wouldn't... So there's extra analysis if you do weird stuff, but we're going to pretend that doesn't exist right now. We're going to pretend that doesn't exist. This means that we're only going to put local variables in here though. Like globals, you're always going to go through weird stack manipulation stuff, just because otherwise it's hard to be safe without... I guess function calls make a nice logical boundary for that. Anyway. So a register is either free, it has a literal, which is just going to be a I32, right? Like a number value in it, a variable, or desired. And we can keep track of this. I guess the alternative to literal is... So there's something else in between these two. Let's get rid of desired. So there's something else in between these two, right? Which would be if we had a chain kind of like this. What if we had the chain of calculations? What if we... Oop, that's my face. We don't want that. What if we had 1 plus 2 plus 3 plus A, right? Where there would be a literal, and then it would be a literal, and then it would be a literal, and then we plus A... I guess let's say plus A plus B, right? So if we're at this point in the calculation, we're not a variable yet, but we're not like... It's like we can't know at compile time what this actual value is. But so we've got a thing we know is a number. It's like a temporary, an intermediate value. Let's call it temp or intermediate. And this is going to have a register associated with it. Maybe a set of registers, maybe... Because it needs to... Hold on, what am I trying to say here? So it's got to... An intermediate value... Like, these things might be registers or they might not. And we kind of need to go ahead of time, I guess, and work out if there are any registers involved. An intermediate value... that... Let's actually just not say it. Let's just call it an intermediate value. Okay, something that's in flight. And let's see if these tools let us do things. Let's just try. So let's impulse state. And let's try making a couple of functions. So we'll say new. Registers. Let's also derive, debug, and default here. This is going to be important because we want this to be the default so that we can just make a default map. Actually, no, not a default map. What's a good hash map constructor? There's a few, right? There's some hash map constructors that we should care about. insert from iter. Yeah, from array. Okay, so let's say hash map from, and this would be register A, and we'll put the default in. I think that makes sense. A, B, C. We'll put M in here as well for now. How about that? Because we're not really using M for anything. That should be okay. Cool. I think that's good. I think that's good. So we've got registers. We can start to reason about them. So, let's say, let's try and get a free register from ourselves, and it's going to give back an option register. Okay, so we just iterate for each register in so for every register, except we want the key and the state. I think we can just iterate over a map like that. That should be okay. If state equals cool. And then we also want to we want an option to set an immediate value in here. Immediate for a register. Now does this return something, right? Do we let ourselves do this if it already has something else? Maybe not. So maybe this should return a result. The result will be let's do result. And maybe return something called a register state error, where we'll say if self registers get R. This is the other thing. There are registers that are invalid. Like we can't set the program counter, right? The program counter is a valid register that we can use here. We can't interact with it in this way. So we do need some kind of safeguards and some kind of error that we can return. So can we get this register? That should be fine. If we get it, if match state, because we probably need to do a match. If it's register state free, then that's fine. Self registers literal. Literal I. Cool. If it's a variable, then this is an error. What does insert return? Insert returns an option V? No, it returns what was previously in there. This is what this should actually return, right? Because, so this has a value, but if I return something here, we'll get mismatched. Mismatched match arms. So I guess I just wrap these in curly braces and then it'll be okay. Return error. Let's see if we can, yeah, so, and this, if we try and put a literal in a register that's already referencing a variable, then this is going to be a problem. We're going to say, this is like a downgrade. And if it's intermediate, then this is the same thing. Excellent. Okay. Otherwise, this is where we return. I don't like this necessarily, and actually maybe this should just return. Ah, that's better. That's way better. Hold on. Get rid of the return keyword in general. I like this. Otherwise, so then the semicolon goes. Otherwise, this is an error. Register. Register. Register state error. This is invalid register. Cool. Invalid register. And then these just need to derive debug. Because I'm just going to debug print though. I'm not going to implement format yet. Okay, so this is good. This is good. So this will tell us if a register is free. This will let us set a literal. Now, now instantly this is looking a little bit problematic. Not problematic, but maybe free should also return if there's just a literal. Let's try this. But this only works if the literal isn't part of the current calculation. Okay, that's not right. That's not right. Maybe after each expression we can reset. But that's not right either because it's recursive. Maybe after each statement we can reset if literals are occupying slots. I don't know. Let's try this for now. This will be more efficient. This will be more efficient. I'm starting to see how this will work. Get. Oh, this, hold on, this mutates as well. I forgot my mut. That's fine. So get variable register. Is this variable in a register? For each register in registers. Var equals s. So if this variable is in a register, then we say okay reg, and that's actually return okay reg, because we want to put a lot of semicolons here and then return none, and just return none at the end. Cool. So we can get the variable, get the register the variable occupiers. We can get a free register and put a literal in there. What else do we want to do? What else do we need here? Register. So how do we say? We need a way of saying when we actually return. So we can't just return this vec. We also need a struct. We need a result. We need a thing that says where the result of that expression went. Did it go in a register or did it go on the stack? We need to be able to ask that. So we need a, I don't want to call it result because result has too much. It's also going to give back a new state. It's also, I think maybe these actually shouldn't be mutable. Maybe they should just copy. Anyway. It should be, what's this called? It's a result. I don't want to call it a result. It's a result by another name. It's a I'm just going to call it expr res, which is a bad name, but we're going to start with this because I don't want to get stuck on a name. This is going to have a destination, which is going to be a and this is an enum, expression destination, which is either a register, or the stack. And it's also gonna bring a new state with it. Cool. So, oh, and it's also gonna have the actual instructions that got compiled, which is a vec of unresolved instructions. Beautiful. So now compile expression should return an expr res. We're definitely going to need some real mean helpers for this. This is probably going to have to be pub crate new. I actually don't know if this is pub crate. Let's just make it private. Let's make everything private for now and then let the errors guide us. So let's say instructions. It's going to take a state. It's going to take... we're also trying to copy these states quite a bit. So I think state should derive... Let's derive debug, of course. Let's also derive clone, because that's going to be important. That also means we need to derive clone here. Cool. Okay, this is starting to take shape. Let's call this from instructions. Because I don't know if this will be the default way of doing it, but this will be the function that will bridge the gap between all the existing code the easiest. Self Okay. So we could actually rewrite everything just using this. And this probably would have been a better place to start, where everything just says stack, right? But I want to try... Oh, crap. This has taken longer than I thought to get here. I want to try something. So this isn't quite right, is it? Let's try get free. The problem is we always need to put the immediate into a register. So what happens if all of these registers are taken up with things? That actually implies to me that register C should not be in here. Register C should be our go-to temporary register that can always be overridden. So let's see if we can do that. So yeah, actually I think unwrap or, I think this is good. And I think it's unwrap or, right? I can never remember the name of this function. Unwrap or. Default, yeah, perfect. So we'll get register C. Except we need to know the difference here, don't we? We need to know... Okay, let's make a tuple. Let's say target and reg is if let sum reg equal... So if we can get a free register, that's great. Then target equals expression target register r, and the register is going to be just r. Perfect. Except we just want to return that as a tuple instead of doing something silly. Otherwise, we say expression target stack and register c. Cool. Now I probably want to move all this into a function, and let's do that. Let's make a function compile expression literal int. So we're gonna pass all of the normal stuff in. It's gonna take a mutable context. It's gonna take a scope. It's gonna take an expression, which is an AST. It's also gonna take, and I'm gonna have to put this on a new line because it's getting a little bit too meaty. It's also gonna take a state, which is gonna be a state passed by value, not by reference. We're not copying anything here. Oh no, we are copying everything here. Sorry, we're not doing lifetimes here. This is gonna get back a result, expr res, compiler error. Cool. Okay, so we're gonna copy this in. We're gonna copy all this in. Not the bit that decides the register stuff, but the rest of this in. Okay, cool. That probably goes back 3 lines. No, 2 lines. Okay, nice. Actually, there's a few things we don't need here, right? Block scope we don't need to pass through. The expression we don't want to pass through. The state we do. The context I actually don't think we need either because this is just a number. Okay, so let's be simpler here. So we're going to pass in the state. We're going to pass in the int value, which is an I32, I think. Could be a U. I think it's a U32. I think we only do we? Sure, let's assume it's an I32. Of course it's an I32. That makes much more sense. Let's call it value I32. So the other thing we need a register to work in, and we need a target, which is going to be an expression destin. Cool. Okay, that's better. That's better. Now this should be expression destination. Cool. Now we do the fun stuff. So this always goes into a register. Let's call it reg. Now we have this branch. If target... Actually, this always ends with this thing. So let's let my out is vec. Let's do this a sillier way, right? Instead of building these all here, let's always end by returning a thing with the vec. Bobbius, welcome. Sorry, this has been a real wild ride. This has been more complicated than I thought, but it's feeling good. I think where the wheels are turning. I'm actually gonna have to go in a sec, sadly. Unfortunately. I missed the add announcements. Oh, I did. I copied and pasted wrong. That's really funny. Amazing. Anyway, it's been a messy stream. Skim through the VOD. That's my advice. Anyone who's watched the VOD this far, you've done a really good job. So instead of this, we're going to say out.push. And then we won't have this hard-coded always push to the stack. So we put it in whatever register we've decided is appropriate here. Whatever register we're working with. And then we get rid of this. And I think I do extend here. I think that works. And now in this case, it's similar as well, except instead of register C, we're going to say reg, and we're going to move this out here. So then after this, we say if target is expression destination stack. If we're putting it on the stack, then we have to do something else. If we're aiming for a register, then we're fine. We're fine, we're done. We don't have to do any extra work. Bolvius says, register assignment's one of those things you've read about but never seen anyone implement. I haven't read about it or seen anyone implement it. That's why this stream's been rough. I think what I've got makes sense. We'll find out. We'll find out if it doesn't work. So this is nice. I need to out.push this, right? So what I'm saying is we do the work in a register, whatever register we're working in, and then if we're targeting the stack, we have to push it as well. If not, that's just one fewer instruction. That's great. That's a free win. We can just pick that one up off the floor. So instead of OK, we're going to say out.extend. Okay. Shit. Unfortunately, I think I'm going to have to go. I was hoping to stream for a bit longer and actually compile something, but we're going to leave this in this weird half-started state. I might concatenate this with the next stream where I do more work on this and actually get something working. That would be good, I think. That sounds like a good idea. When I put it on YouTube. Or I'll just dump this up there and people can come and look at my plan. Here's my plan, Bobius. Here's what I'm doing, right? Here's my hand-compiled example where I thought about where various things get... I think it's called coloring, right? Where you're like, what's this being used for? B has a literal in it. So then later on when I'm trying to work out where to assign something here, or if I can assign something here, I'm like, hey, B just has a literal. Let's associate this register with the variable B. And then at some point, I should go through and work out if these variables stay relevant. Like, you know, A isn't used anymore, so we can reuse that register for other stuff. But that can come later. The step where we actually go through and work out how long this register needs to be associated with a variable. So it's a very greedy algorithm at the moment. It will be horrifically bad for big functions, but it'll work well for small functions. And for big functions, we can be smarter as we go. You'll always be able to write code that makes it do dumb stuff, because, of course you will. That's how optimization works, right? If you write weird code. Like, I'm not going to do lots of analysis. That is an exercise for the reader, anyone following along at home, if you really, really want to. My goal is to make it good enough that it's okay, because right now it's just really stupid. Anyway, I am going to have to head off, unfortunately. Thank you very much, everyone who's been hanging out. I don't think I have time to do a raid. I really gotta make a move. So thanks for hanging out. Good to see you, Bobius. Thanks everyone who's been watching. Hope this was interesting, and hope this journey of optimization is going to go somewhere really good, because it was a bit of a rough start, but we'll see if we can do something fun. All right, awesome. Catch you next time. Bye.